what it takes to address the cloud, what's causing the cloud to increase, and the types of chips that we need to build to be able to support that. eSilicon is also not only an ASIC provider, but we're an IP provider as well. And so we're going to cover some of the IP that we build to differentiate networking and communication FinFET ASICs. And this IP you can see on ChipEstimate.com. So let's take a look at the cloud and what's fueling it. I took this from Cisco's VNI global IP traffic. It shows the expected global traffic from 2015 to 2020. And what it shows you is that there's going to be a 3x increase in 2020 up to 195 exabytes of data. I mean, that's just huge. I can't even imagine what that looks like. And what's driving that is basically we've got more devices that are being connected. We've got faster broadband speeds. And, of course, more internet users. And we all love video, everybody. So we're posting video, watching video, and so there's just a lot of data traffic that we're having to manage. So what are the design challenges to be able to achieve that when we're looking at it from a system level now? We're going down a little bit. So we're doing, WAN redesign, moving applications to the cloud, for example. And then if you look at the 2016 Ethernet roadmap, you can see that, we're migrating from 40 gigabits per second to 400. And what you'll see is shortly down that road, we're going to be at a terabits per second. So a lot of activity on the Ethernet side of things and on the Ethernet roadmap. And then because we have so many new people using the internet, so many more users, our protocol, IPv4, is running out of steam. It's running out of numbers, basically. And we're having to migrate to IPv6. So these are things that are having to be managed from the system level that are further driving us at the ASIC level and the types of designs that we do. So what do these chips look like that are trying to address the items that we've talked about in fueling the cloud? So data centers are comprised of networking, storage, and compute. These chips are very, very large. And data centers are really trying to manage the cloud attributes, if you will. So there's a lot of complexity in these chips, and they have a lot of features. If you look at the chart at the bottom, not the chart, but the figure, you'll see an ASIC with 4 stacks of HBM memory. This is high bandwidth memory. These chips are typically greater than 400 millimeters squared in area. And they typically have 1 or more stacks of external HBM memory on an interposer. So they're fairly complex. From a technology perspective, what's needed is to be able to move at very high speed. We need process technology that'll support running at 2 gigahertz at worst case, for example, while managing power. And also very dense SRAM technology, because these chips typically have 900 megabit of embedded SRAM of various different flavors on board. TCAMs, they have various different multi-port register files, for example. And so there's a very significant amount of interconnect and parallel lines that have to be routed as well. And SerDes, a significant amount of SerDes on chip as well. This is a chip that we've done recently. This chip is in production. It supports 3.6 terabits per second. You'll see that it has an ASIC. This ASIC has 1 HBM stack that's 4 high. It's 150 million gates, and you'll see also, like I was saying, a very significant amount of embedded memory on this chip. It also has 60 lanes of SerDes, multi-protocol SerDes, up to 28 gigabit per second. And some of the eSilicon IP that's on this chip is the HBM PHY that is interfacing with that HBM stack. Of course, memory compilers that are very specially designed to really meet the characteristics of networking and communication. We also find that, because there's so much memory on these chips, that it greatly affects the specifications that you're trying to achieve. So in many of our ASICs, we actually will do some sort of optimization for one or more instances, really to try to hone in on really meeting or beating the spec that we're trying to achieve. And then, of course, a ternary CAM. So this is a pretty busy chart, but it gives you several examples of how we differentiate ASICs. These are different ASICs that are almost all of them are in FinFET technology, and they are in the networking or machine learning space. So I'd like to highlight a couple of things from here. If you look at the second row, for example, this is an ASIC that's currently in development. It's a 7 FinFET design. And it has pretty much all of the IP that we build at eSilicon. It has an HBM PHY. It has very fast cache SRAM. It has these dense multi-port register files. And really, the use of some optimization, as I was mentioning earlier, where we went in and optimized certain instances, we were able to increase the speed by 20%. And then, of course, the HBM itself is operating at 2.5 gigabits per second. Now, if you segue down and take a look at the last row, for example, this is in a machine learning market. This is on 14 nanometer. And this highlights a little bit more of these custom multi-port memories. So to really achieve a dense multi-port, what we use is a 6T SRAM bit cell, and then we double pump it. This is not new. Many people do. But to achieve 2 gigahertz operation, that means that 6T SRAM bit cell, that memory underlying all of that, has to be running close to 4 gigahertz. I mean, that's huge. So there's a lot of design work that has to go into it, as well as having the foundry providers having processes that will support that type of speed. One other highlight I'd like to take here is in the third row. And this is an example of something called HBI, or high bandwidth interconnect. A lot of people call it chip-to-chip interconnect. And what we were able to achieve here is we had a very large ASIC that we were able to partition into 2 ASICs or more. And what this did is it enabled us to save on the cost and improve the yield by partitioning it in that way. And so what we did is we leveraged the HBM PHY, and we were able to use components of that already silicon proven PHY to be able to communicate at even faster speeds than for HBM technology. So this was a significant benefit for this particular design. All right, so 2.5D, how does this really increase bandwidth? Well, if you take a look at a typical system, it'll have an ASIC with multiple DRAMs that have to be packaged around it, DDR4, DDR5, etc. And so with this, you have a latency issue, you have a power issue, and you have a real estate issue. So that's really what's driving moving to having stackable memories, which you can see on the right. The green is the interposer. You can see 2 stacks of HBM memory with the ASIC. So what this does is greatly improves, the footprint and the power, as well as increasing the bandwidth. Because think about all of the parallel signals that you're able to route from that ASIC to that DRAM stack at very high speed. So now, if you want to take a look at HBM and the communication, the parallel communication that you have to the external memory stack, if you look in the upper right, some customers we're finding actually want the ability to be able to have a PHY that'll enable them to communicate to an external DRAM, but also they have some chip-to-chip communication that they want to do as well. So having a configurable or a combo PHY that can support both of those is desirable. And that's really what we've done, is we've incorporated the ability to support both. And when you're transitioning from HBM to HBI, basically you're able to leverage the I/O. You're able to leverage the bump pattern. You're just reassigning some of those bumps. You're using the IEEE 1500 for test and repair. lane repair. So a lot of synergy between these PHYs that enable you to be able to do these types of combinations. This is just giving you a little flavor. Since eSilicon is an ASIC company and an IP provider, we've been studying 2.5D for a long time. We've been studying it since 2011. We've run a significant amount of test chips. We're in production today with an ASIC with 2.5D. So besides building IP that you'll see on ChipEstimate, we also do interposer design and the things that are associated with that, the signal integrity, the power integrity. You'll see in the upper left the warpage analysis of the package, and in the upper right you'll see the bump pattern as well. So it's really a full service. We have that understanding, and when we're building the IP, of course that's being incorporated into the IP that we develop. So last but not least, I just wanted to highlight our TCAM. So TCAMs are SRAMs basically, but they have some additional function to them. Basically what a TCAM does is receiving a search word, it's basically going to respond with a matching memory location. I mean, really boiling it down to something simple. And if you look at, we were talking about going down that road of Ethernet going to a terabit per second. At that point, all of the operations they have to take place, have to happen with 2.5 nanoseconds of time. So just think about that. All the functions, the parsing, the classification, and forwarding, all of these things have to be completed in that amount of time. And TCAMs really provide an order of magnitude benefit when you're actually taking a look at this performance factor. These are 3 areas where TCAMs are heavily used for MAX, switching, and packet processing. And if you think about an ACL, for example, ACLs really are controlling what's passing through to particular ports in a system. And it's the TCAM that is actually doing that within an ACL. And you'll see that this has a significant amount of TCAM involved in packet processing. And this is exactly the area when I was talking earlier about IPv4 and IPv6. If you had a 2K word by 288 TCAM, that supports both IPv4 and IPv6 operation. So our TCAM, the range of the compiler and the way that it's been developed, we make sure that we're able to support both protocols so that customers are able to build their systems and be able to manage that transition from IPv4 to IPv6. This is some examples of where eSilicon's TCAM resides. These are some customers that we have, largely in FinFET technology, but also in 28 nanometer. You'll notice that the amount of TCAM incorporated in these designs is increasing significantly. And they're used in the same operations that I was mentioning to you in the previous slide, for the MAC, for the ACL, switching, etc. We do offer a priority encoder. We do manage ECC as well with our TCAMs. And we've been building TCAMs from 180 nanometer, and we're now developing 7. And I'd just like to point out that, the fact that we are an ASIC company and we use our own TCAMs, we have skin in the game. So that TCAM will take us right out if it's not developed properly. And also we really understand the performance and power characteristics that are necessary for these types of systems. Because while they are higher performance and we're putting more and more features on these complex chips, the power budget is still rather stable. These things still have to fit in the racks, in the data center, and that's not really changing. So for eSilicon, from an enablement of networking and computing, we have a whole platform of IP that's available on ChipEstimate.com. You can see Samsung 14 LPP is fully available and silicon verified. We have a portion of the IP available on 16 at TSMC, and the whole platform and more is being migrated over to 7 FinFET at TSMC. This includes all of the TCAM, the multi-port architectures. There's some new interesting ones that are being built at 7, the chip-to-chip interconnect, and the HBM PHY. So come see us at ChipEstimate.com or at eSilicon.com.